Okay, so yeah, welcome to the first session, the first paper of the winter semester in the reading group. Yeah, today I'm going to talk about Starburst. Starburst, a coast-aware scheduler for hybrid cloud. So I think it's a decently simple paper that talks about scheduling, and it talks about private cloud and public cloud, and how can we leverage, the private public cloud together to save money, right? So let's pretend that we have, a private cloud, which is kind of our own data center. And in that cloud, we have some resources, right? So, some number of servers that have CPUs, GPUs, and whatnot, right? The point is, because it's our data center, the amount of resources is finite, right? So you can only do so much stuff in that in your own private cloud. The plus side is it's cheaper, right? Because you already have that hardware, right? So, there is obviously like upfront cost and whatnot, but supposedly, according to the paper, if you have the private cloud, it's cheaper to run, your private cloud, right? You already paid for the hardware, so you better use as much of it as possible, right? But, because it has finite resources, if you want to do a lot of stuff, if you have a lot of things to compute, you may need to spill over to the public cloud, right? And of course, public cloud sells you that illusion of infinite resources, right? So you can keep scheduling more and more and more things, and the public cloud supposedly will oblige and give you more and more and more resources, and charge you more and more and more money, right? So the downside is, again, it may cost you more, right? Compared to your like fixed cost that is your private cloud. So, the users submit jobs, and in the context of this paper, we're talking about a long-running analytical type jobs, so machine learning type jobs. So things that take quite some time, right? So the users, will submit the jobs, and supposedly these are the users in your organization, in your company. So logically, they will be in a private cloud in your own data center, and they will submit this batch computation that requires, in my case, 2 bars of resources, and we'll submit it. And since our private cloud at this point is empty, the private cloud can handle that job just fine, right? And then, more jobs come in, and we keep adding them into our private cloud. And at some point, you may end up in a situation where you want to submit more jobs, but you don't have any available resources, or not enough available resources in your private cloud. So what do you do then? Right? We have this lovely public cloud, which is costly, that can handle that particular batch computation. So one solution is to take a look at your private cloud, realize that you have no capacity in the private cloud, and without waiting, ship that computation, ship that job to the public cloud. And that way, all of your computation tasks, they are running as soon as possible, right? Of course, you are paying a little bit more money for using that public cloud. So that's one solution. And according to the paper, the authors claim that that's the typical solution that people would use in that scenario right now. But the big question is, are there any better solutions? Like, can we save money, right, by using that public cloud less, but still not take forever to compute, to like run all these jobs? And the proposed solution, the big idea is like not groundbreaking here, right? We can just wait a little. So if we have this job that comes to private cloud, that comes into our system, we don't have enough resources in the private cloud, instead of sending it to the public cloud immediately, we can queue it up, right? So put it in some kind of queue in hopes that some other job running in the private cloud will complete soon and free up enough resources, and you can then run your job that's in the queue in the private cloud, saving money. And again, ideally, you don't spend a lot of time in that queue, so you're not adding the latency, right? So you're not increasing the job completion time. So we want it to be in a queue to save money because we want to wait for the resources to free up and run private cloud, but we don't want this job to be in a queue forever because we don't want the completion time, we don't want the latency to grow by much. And again, for the context, I'll repeat it again. In this paper, we are talking about very large, long-running types of jobs, right? So they talk about jobs that run in the duration of hours, right? So we're not talking about latency of milliseconds or seconds. We're talking about latency of hours to complete, right? So if you keep this job in the queue for a minute or two until some resources free up, compared to maybe a runtime of this job of 3 or 4 hours, that's practically nothing, right? So yeah, if more jobs come up into the system, you will add them into the queue, and eventually, you will have some resources free up, and you can take, the stuff from the queue and start running them. So that's the basic idea, right? Now, if your data center is very overloaded, of course, that queue can grow very long, right? So the depth of the queue becomes big, and everything in the queue starts to wait very long, right? So you don't want to wait forever. And what do you do if things start to happen too long? If you wait too long, you set some kind of timeout on waiting, right? So if this job has been sitting in the queue for quite some time, the timeout has elapsed, then you ship it to the public cloud and you handle that job in the public cloud, right? So you kind of want to have a compromise, the best of both worlds, right? Try to use the private cloud as much as possible, and you increase the chances of using your private cloud as much as possible by waiting a little bit. But you don't want to, wait forever, right? You wait some amount of time, and then if nothing frees up, if you don't have resources in a data center in a private cloud, ship it to the public infrastructure. So the big question that the paper tries to answer is how long do we actually have to wait, right? So none of that stuff is really groundbreaking, that the stuff that I described. The big research question that this paper tries to answer is how long to wait. The simplest one is a static wait, right? So wait for some constant time. You just figure out some wait time, and if no resources free up in that time, send the job to the public cloud, right? So, but then you need to fine tune this constant time, right? And what is appropriate wait time will depend on the size of your data center, the types of jobs you do, and so on and so forth, right? So, this static wait may actually require quite a lot of fine-tuning by experts and whatnot. So the alternative approach is dynamic wait time. So let's build the system that can figure out how much time each job in the queue needs to wait before we can push it to the cloud, to the public cloud. Right? And this paper claims that the definitive parameter that determines how much you need to wait is job size. And when they say job size, they mean actually the job size in multiple dimensions, right? So how big the job is in terms of the resources it will need, right? So if the job asks for 20 GPUs versus 2 GPUs, right? That's the one dimension of the size, right? So bigger jobs ask for more resources. But also the runtime, right? The duration, how long does the job actually run in the environment, right? So that's the second dimension of the job size. So if you have bigger jobs, you may want to wait a different amount of time. The paper claims that the most cost that you can have in those kinds of systems is due to big jobs, right? So and because of this, it makes sense for the big jobs to have to wait a little bit longer to have the chance to run in the private cloud, right? So essentially, you want to give the big job a bigger wait time so that it maximizes its chance to run in a private cloud for cheap, right? So the paper presents a formula that they use to compute the duration, and that formula accounts literally how long the job is expected to run and how much resources the job is request, and some tuning parameter. Another issue, though, that kind of starts to show up if we have big jobs that wait for very long is the head-of-line blocking, right? So if we have a big job that sits in the queue and it's waiting for a lot of resources to free up in a private cloud, it will block all the other potentially smaller jobs that can run in the cloud, right? So we're actually hurting the utilization by having that big job not schedule it anywhere and just blocking the smaller jobs, because the longer time is going to elapse, the more resources on the private cloud is going to free up, and they will see it free until that big job finally has enough resources, right? So we want to avoid that head-of-line blocking in case we have excessive queuing, right? So in case the queue is large, that the depth of the queue is getting big, we don't want the large job to just block everything. So what they do is they reorder the jobs, right? So the first thing is obviously the length of the wait time depends on the job size, right? So smaller jobs will time out quicker and will go to the public cloud quicker if they need to, right? But the second part is reordering inside that queue inside the private cloud. So if we have small jobs that kind of sit behind the big jobs, we can simply loop through the job queue and greedily schedule any job that can fit, right? So it's kind of not really like a job queue anymore. It's more of a job list, right? And you just picking the stuff from this list that will fit in your current amount of free resources in the cloud. So with all of this, essentially what we end up is having a system that prioritizes the jobs differently, right? So bigger jobs, even though it may arrive, this big job arrived first, but it moves out to the public cloud if nothing happens at much later time because it's a big job. Maybe this small job, even though it arrived, after the big job, its expiration, its eviction time to the public cloud is before the big job, right? So if nothing happens here, this orange job will go to the public cloud before the yellow job, right? The job size determines, the wait time, but also, I guess I'm missing one slide. But if some resources free up, maybe enough resources free up for this orange job, like this job goes away, so this resource become idle. Now this orange job can potentially, run in a private cloud, even though it's kind of sits behind the big job, and the system will let it do so, right? And at some point, if nothing else happens, you will have to move some jobs to the public cloud. But again, you move out, like you let the bigger jobs stay longer, right? So you potentially may again move out the smaller job because it has the sooner expiration time to the public cloud. So one big question is, how does the system know like how long a job takes, right? So we can kind of get the amount of resources a job requires from a job description potentially, right? So, you will specify the job to say, I need 10 GPUs and whatnot. But how long is it going to actually run? So the basic algorithm, uses that time, to figure out that eviction time essentially, right? The time at which the job needs to go to public cloud. But like, how do you know how long the job is going to run? So for one, you can kind of maybe use the historical data, right? So if you know that you're running similar types of workloads, maybe the same batch size, similar data, the same computation, right? So you can kind of use the historical data to figure out what that particular batch size for that job is going to take. But you can also do this, right? So the other version of their system, if no information is available on the job runtime, like how long it's going to take, the second version of their system will just will start the job in the public cloud. Like it will not queue up; it will send it to the public cloud, and then run it. And if it takes too long to run, then it will stop it and move back to the private cloud and put it in a queue. And with this system, all short-running jobs, they can complete in the public cloud. Obviously, it's going to take some, cost, but they're short-running jobs. And they define this threshold as like 1/8 of average like job runtime, right? But for the longer jobs, if it runs too long, okay, don't run it on the cloud until completion, right? Save it, checkpoint it, whatnot, move it back to the private cloud, resume in the private cloud whenever the resources become available. So that version, if you don't know the runtime of your jobs, if you cannot approximate that, is a little bit less efficient, but the author's claim is still pretty good. And yeah, onto the evaluation. This figures look at the real workloads. It look at the traces of the workloads, and they have a private cloud, public cloud. The x-axis is the system load expressed in the private cloud's capacity, right? So if we're looking at system load of 1, that means that you are submitting as many jobs as a private cloud can handle. Right? So 0.5 means your private cloud is going to be idle. 1.5 means you're sending more work to the private cloud than it has the resources. 2.0 is you're sending twice as much work to the private cloud, like to your system, as the private cloud's capacity. Right? So obviously when the private cloud is underutilized, right? So you're not like using too much of the resources. It makes almost no difference like on what strategy you use, like the Starburst system, or constant wait, or like no wait. They take about the same time because you can always run things in the private cloud, right? So there is no need to ever figure out like, do I need to ship stuff to the public cloud? Because, well, you don't need to ship it to the public cloud, right? It's like your private cloud is available. But as you get, as more resources start to, get used in the private cloud, the queuing effects start to add up, right? So you may end up in a situation where some resources are available, but data center, but you cannot run the job either, right? So in those scenarios, obviously, having to wait a little bit starts to help you, right? So that's when Starburst, the red and the purple, will save you money, right? And the constant wait saves you a little bit, but not that much, right? So the power of dynamic wait whenever you have the whenever you're like in this sweet spot between 0.5 utilization and 1 utilization, right? Or not utilization, the load, right? So if you're asking up to like your private cloud's capacity, dynamic wait can save you a lot of money because the time, right? Like obviously, if we don't have the public cloud and we allow everything to queue up, you save all the public cloud money, right? You'll spend zero on public cloud, but your time to completion is gonna increase, right? So, and that's where we have those this figure, the figure number 3 here. So that's the average job completion time in hours, right? So no wait is the policy that engages the public cloud right away. So that will be the policy that offloads everything to the public cloud as soon as the private cloud cannot fit the job, right? So that will give you the best completion time. That's the optimal case. And what we see with Starburst is, it does increase the runtime, right? Compared to the savings, it may be worse to you, right? It depends. Similar situations with like other workloads and whatnot. And the paper has more evaluations, but I will stop here.